So I thought I would talk two things today. Provide an overview of what Nexa is, and then talk about an application which I call Atomic Secret Exchange, which would allow you to create effectively private NFTs. Okay, so my personal mission in creating Nexa is to have cryptocurrency for everyone every day, right? Like Bitcoin has become a digital gold. And I don't know if you recognize me, but I was a significant part in my organization, Bitcoin Unlimited, was a significant part of the fight to attempt to scale Bitcoin way back in 2017. And we didn't succeed at that, so we subsequently worked in Bitcoin Cash, and now we're creating our own cryptocurrency. And this is what I would like to see cryptocurrency actually succeed at. So that's what we're working on. So let me give you a brief overview of what Nexa is. First of all, it's a UTXO family blockchain, as in coming from the Bitcoin family, the Bitcoin world, not the Ethereum world. It's proof of work, peer-to-peer, decentralized, anonymous, permissionless, right? So it's as I tell my students, it's like a real blockchain. It's not like a buzzword chain that tries to, jump on all the, the hype. All right. 10-minute blocks is a long time. We just quickly dropped that down to 2 minutes. It has something called double spend proofs. So the end result of that is if you're a merchant and someone tries to cheat you, right? You'll get a notification on your phone or your POS device right away that someone is trying to, double spend the payment to you. And then, it's a 2-minute wait on average, before there's a confirmation. So, the performance is already a lot faster. And what I mean by that is Bitcoin Unlimited, the organization, that I work for, or I, the founder, didn't get any initial coins. We did a similar release as Bitcoin, where the Genesis block commits to a piece of news that happened that very day. So everyone had the chance to start mining a few years ago when it started. We also follow sound money precepts. We chose to use Bitcoin's mining reward schedule just to make it obvious, and also because Bitcoin has been basically accepted, not as a security for a variety of reasons all over the world. And so by using the same coin tokenomics, we're able to take advantage of all that knowledge, right? But the one difference is that one Nexa is just 100 of our finest unit, which we also called Satoshi, whereas a Bitcoin is 100 million, right? So basically, if I talk about, 2 million Nexa, that would be effectively the sort of, quantity equivalent of 2 Bitcoin. Obviously, though, the price is very different. So don't worry about that. Okay. So one thing that we chose to do is use the UTXO architecture instead of what you guys may be more familiar with, the EVM architecture, right? And there's important reasons for that. I feel like the UTXO architecture hasn't been explored that much. Development effectively stopped in Bitcoin. But there are some tremendous advantages for an everyday cryptocurrency in the UTXO architecture versus EVM. So if you're familiar with EVM, this is kind of the slide for you. So first of all, we can do massively parallel evaluation of transactions. We can execute the scripts in a transaction exactly once. We don't have to execute them once to see if they might work, and then again when a block comes in. And the reason why is because a transaction specifies the exact state that it's expecting the ledger to be in when the transaction is executed. And if that ledger state has changed, the transaction is invalid. And the end result of that is you have these usability and security advantages. First of all, you may have heard horror stories about MEV in Ethereum, maximal extractable value. This is where a miner will front run your trade or something like that to extract money from you. You can't do that in Nexa because a transaction relies on specific UTXO state, and if you front run that, the state simply changes, the transaction is invalid. There's no blind signing problem, and that is where you sign up to connect your Ethereum wallet with a website, and you think that it's going to you show it your token and it's going to give you another token, but instead it just steals your money, right? So because a transaction specifies exactly how it's going to change the ledger, not in a programmatic way, but just in a delete these entries, create these entries, the blind signing problem cannot exist because a wallet can simply say, this is what is going to happen in the transaction. So here's an example of our wallet. And it basically says, hey, in this account, we're going to deduct 25 million NEX, and you're going to get an asset. And that's what's going to happen. There's no way to cheat that transaction. There's no way to change what would actually happen to it. Another thing that we do is, like in Ethereum, I don't know if you guys have coded Solidity and like ERC 721 or 23, but you are essentially implementing your own tokens on top of their distributed computer, right? But Nexa, so Ethereum is more like a massively redundant computer that you can layer finance on top of. Nexa is more like a financial blockchain that has computational abilities, right? So in particular, the blockchain itself has tokens as a native feature of the blockchain. So it doesn't just have Nexa. It has, you can create your own token, but then once you do, the blockchain will enforce issues like quantity and proper transfer. And because of these issues, and because the scripting system is as it is, you don't really have the gas problems that you typically do with Ethereum. No need for gas. All right, one second. So we did, we have been working on the ultimate Bitcoin source base since 2012, right? But to call us a fork of that source base is, we've spent years upon years working with the source base, right? So we have tons of advances in performance and scaling, native tokens, these multi-party interactive transactions, which I don't think many other blockchains do, and then also blockchain and network enhancements. So in scaling and performance, in our tests, we're capable of doing 50,000 transactions per second, right? And this isn't like in a lab. This was between computers in both Italy and Canada. So I'm not talking about some custom hardware. These are normal computers running in people's houses, communicating over the open internet. Yes, and then you can see it took a little bit to ramp up our test, but there we are at 50,000. And there are reasons why. We have this massively parallel transaction admission technology, which basically looks for transaction conflicts by using a Bloom filter, which I talked about quite a few years ago at a Scaling Bitcoin conference. Scripts are executed once, as I referred to previously. There's also some optimizations to minimize the UTXO size. So in this slide, I just want to throw out a whole bunch of features that we have implemented. It's definitely not an exhaustive list. If anything like catches your eye, you can come talk to me later over in the Nexa booth. But one of the most important ones is these native tokens that I'm talking about. They both, they move the blockchain both to a medium, like Bitcoin is effectively a medium of transfer, right? You can transfer Bitcoin to someone. But if a blockchain is a language, it has verbs, right? But to have more than one noun, you need tokens. You need to be able to specify more than one thing, right? So having native tokens is critical to that. So now all of a sudden the Nexa blockchain becomes a medium of exchange. I can atomically trade a token for 3 other tokens and some Nexa, right? All right. So we've taken that and kind of fleshed it out, and we have what I call multi-party interactive transactions. And these are not like contracts yet that exist on the blockchain, okay? The idea is, if say Alice wants to buy 100 of token T for 1 million Nexa, then she'll create a transaction and sign it, giving herself 1 million Nexa on the input, and then taking 100 of token T, right? But of course, that transaction doesn't balance, right? As I said before, like the Nexa blockchain enforces quantity as a primitive, right? So this is an invalid transaction. But it doesn't matter. She could just throw that out to the internet, and then someone else might say, oh, well, Bob might say, well, I don't have 100 T, but I have 50 T, and I have 50 U, and I'm going to take some money. So then Bob will extend the transaction, right, and sign that part of it. And then, in practice, 99% of the time, of course, someone just solves the transaction right there. But really, I just kind of wanted to show an extended example. Now you have 2 simultaneous partial transactions floating around on the network, and then anyone else, say Carol, can be like, oh, I can solve this entire transaction, make all the money balance by, adding 50 T that I own and taking the 50 of token U and then taking the leftover Nexa. So this is something that is, I think, very different than most blockchains, right? We're not talking about a contract that's executed on-chain. We're just talking about an anonymous interaction between parties who are collectively building transactions without them knowing who the other party is. And the end result of something like that is basically like a de facto open outcry exchange, which is a word for what happened in the olden days in initial stock markets, right? When people would shout out, "I want to buy so much of X," and then someone else would say, "I have that," right? And then they would get together. So what's cool about this is it's a ad hoc exchange. It can be atomic, permissionless, anonymous. There's no intermediaries. There's no single blockchain contract, right? So it's not like Uniswap is providing a contract that authorities could subsequently target. It's individuals creating partial transactions and placing those transactions anywhere in the world, right? Place them on social media. This little QR code there is an offer to sell that NFT pictured for 25 million Nexa and gaining 1 asset. And previously I showed what would appear in Wally in a previous slide if you scan that QR code. And this I captured from Telegram, right? So the end result of this technology is basically, with blockchains, your currency is fundamentally information, right? And so communication of that information becomes transaction, right? And so that implies that freedom of speech implies, without any way to prevent it, freedom to transact, which I find very powerful concept, right? And effectively proof that blockchains are a fundamentally more powerful form of money than previously invented. All right, so that's kind of an overview of Nexa. And for the last, any questions about Nexa? Anyone want to throw out any questions or comments? Yeah, so it is a proof of work blockchain. So it's currently mined with GPUs. Yeah. Any other questions? All right. So I'm going to go kind of pretty technical and mathy now. So what I want to do is talk about how you might implement a novel function on Nexa. And the problem that I want to attack is how to sell a secret, okay? How to sell like a secret. This is actually not something you can really do in real life, right? Because if I said, oh, I have a secret to sell, and then the person would say to me, okay, I'll pay you $50. What's the secret, right? And they go, oh, the secret is 42, right? And you say, well, that's not the secret, right? The problem is that it's not atomic. I paid the money, and then the person could lie to me about what the secret is, right? So what we want to do is create a trustless, anonymous, permissionless, and decentralized manner to create an atomic exchange of both assets and like an extra blockchain idea, which is a secret, all right? And of course, the blockchain must verify the continuity of the secret, right? They must verify that you're not lying about the secret, and more importantly, that if I buy the secret from someone and then I resell it, I don't lie about the subsequent sale of the secret. And it must be able to do that, and it must verify the secret was transferred without actually gaining knowledge of the secret itself, right? So, like, that's sort of like my little icon, right? How in the world can a blockchain, without knowing the contents of a secret, actually verify that the secret was correctly communicated? So let's go through it. So to think about this, you need to understand some cryptography. So this is like an insanely fast cryptographic review, okay? So it's basically cryptography in blockchains is based on elliptic curves, so which are they form what's called a mathematical group, okay? And what you need to know about mathematical groups is it's like second grade math, okay? You've learned how to add, and you've learned how to multiply, but you haven't learned how to divide yet. And in fact, the key part is that division is completely unfeasible, okay? So we have what's called a trapdoor function. All right, so basically you can figure out capital X here, but if you're given capital X and G, you cannot figure out little x, which is the secret, right? Okay, so based on that, on top of that, we have this well-known protocol called Diffie-Hellman key exchange, right? Some of you might be familiar with it. It's often incredibly confusing, but if you actually think about how it works, if you use like your computer brain, not your math brain, and you break Diffie-Hellman key exchange into layers, you realize, oh, there's a layer that forms the mathematical group, and then the key exchange itself is actually quite simple. So what happens is, and what Diffie-Hellman key exchange lets you do is it lets you communicate a secret over, or it lets you and someone else create a shared secret over a public channel without any eavesdropper discovering what that secret is, okay? And the way it basically works is Alice picks a random number A, and Bob picks a random number B, like little b, and they both create this capital A and capital B, okay? Those are called their public, secrets, basically. And they exchange capital A and B over public channels. Now, as I said, for a group, because of the, precepts of group theory, if anyone gets A and no G, they cannot divide and get little a, right? But Alice and Bob can figure out a shared key by doing a group multiplication of, for Alice, her private little a secret and Bob's public one, and then Bob can take his private value and multiply it by, Alice's public secret. And so then they both come up with the same number. But an observer cannot come up with that same number because, it cannot do the division. All right. And then the final piece that you need here is Schnorr signatures, which I've just summarized really quickly. A signature, and Schnorr signatures work in Bitcoin, right? They're very standard stuff. Is you have your signing key, which is X. You create a private nonce and a message, and so this is Schnorr signatures. All right. So what I'm going to do is I'm going to use Diffie-Hellman key exchange to create a shared secret nonce, and then you might think, oh, let's just communicate the secret, right, over this, we can use this other Diffie-Hellman key exchange secret to encrypt the NFT secret and send that, right? But that wouldn't work because then once I've sent the secret, why would the person pay me, right? So I can't actually do that. What I do, though, is instead I send the secret nonce of Schnorr signatures, which is K, to the recipient of the secret. And then, so the purchaser creates an offer that requires a signature that uses this public nonce, capital K, and the actual NFT secret. And then the seller signs the data with the secret and this agreed upon nonce and posts it to the public blockchain, right? So from the public's perspective, this just looks like a signature validation, right? So what we've done here is I've basically provided a little bit of information to one individual so that in the process of a protocol, that individual can effectively break Schnorr signatures, recovering the secret that I wanted to communicate, but everyone else just sees this as a normal Schnorr signature. So the purchaser uses the signature that was published to the blockchain in the atomic transaction where I paid, the seller paid, the seller received the money and the purchaser received the NFT with the secret. And the signature is revealed publicly on the blockchain and verified, but only the purchaser can actually use that to discover the NFT secret. And they do it with this math. Okay, and over on the right here are all the Nexa Technologies that make this happen, unique stuff. Okay, so this is how we implemented this on Nexa. So the buyer finds the seller and agrees upon, the Diffie-Hellman key exchange nonce. The buyer makes an offer, the seller accepts an offer, and then all that's needed is a special contract to enforce the qualities that I described previously. And this is the contract code. If you happen to have written a Kotlin-based specialized language to compile into Bitcoin or Nexa script. So there it is. What it basically does is it says, hey, we need to find some information to sign, and then we're going to do a signature verification of the the NFT secret that's discovered with a challenge. I don't really want to go over all the details, but the question is, what would you use this for, perhaps, right? And so there already is a blockchain out there, for example, called the Secret Network. And what it does is it uses like a trusted execution environment to place their entire blockchain in like a private space, okay? But the problem with that, though, is that trusted execution environments have been exploited and they are exploitable. And so if you have an entire blockchain and your secrets are hidden inside that blockchain, one exploit of one trusted environment in one place can recover all of the secrets in the blockchain. However, what this system would do is allow every individual to hold their own secret. And so if you were to exploit a trusted execution environment, then all you'd get is the one secret that you happen to have. So it basically is like a distributed way to store and communicate secrets. What I would use this for is anything that requires some kind of digital rights management. Like these days, I don't know about you guys, but I hate to buy like electronic media or books because I always figure, well, what's going to happen if I lose my login to Amazon or whatever, some other company goes out of business, right? And also, I can't sell those books onward because it's just I've gotten permission and I supposedly own that media by this centralized company whose app might go out of business, their app might go bad, it may not run on my computer and so forth, right? But this would allow a decentralized way to move and trade your ownership of these sort of media assets. So that'd be one possible use. I think there's lots.